Welcome friends to my YouTube channel Somo Physics. Now yesterday's lecture I shall discuss about latent heat equations, and there I told first and second latent heat equations, and also I told the effect of pressure on boiling and melting points. Okay, now in today's lecture I shall going to discuss about Ehrenfest equation. Okay, that is Ehrenfest equation. What is this? In today's lecture, at first, I am going to discuss Ehrenfest equation. Okay. So, this is a equation that involves second order phase transition, and we will also discuss in this in next chapter, that is in phase transition chapter. We will also learn it that there are two type of phase transitions, first order and second order. Okay, so in first order phase transition, entropy and volume does not remain constant, but in second order phase transition, entropy and volume remains constant. So this we will learn in next chapter, but now today just you remember that in second order phase transition, second order phase transition in second order phase transition, entropy and volume remains constant. Okay, in second order phase transition, entropy and volume remains constant, so we have to take both. So let us assume at first the constancy of entropy. So at first assume the constancy of entropy. Okay, that is, so you can choose entropy as a function of pressure and temperature. Okay, you choose entropy as a function of pressure and temperature. Okay, since we are assuming the constancy of entropy, we assume S is a function of pressure and temperature. Okay, so since ds is a perfect differential, what we can write, since ds is a perfect differential, what we can write, we can write ds, that is del s del p temperature constant dp plus del s del t pressure constant dt. Okay, so from Maxwell's relation, what we can write, we can write del s del p temperature constant means minus del v del t pressure constant, and this is simply t into multiplied by 1 by t, that we can write, so del s del t pressure constant dt. Now what we can write this equation, now we know that volume expansion coefficient, we all know that volume expansivity, we all know volume expansivity alpha 1 upon v del t pressure constant. So from this we can write this term as minus v alpha dp plus this we can write t del s del q del t cp, that means this. So this can be expressed in terms of this. Okay, this is what alpha means, increasing volume per unit rising temperature. So this is alpha equals to 1 by v del t pressure constant, from which this term can be written as v alpha, and this is cp by t, because we write this term as t multiplied by 1 by t, and t del s means del q, and del q del t pressure constant means cp dt or cp, and there is a dt term. Okay, there is a dt term. Okay, so there is a dt term. Okay, dt term. Now I told earlier that in second order phase transition, entropy remains constant. That means entropy of the initial state this must be equal to the entropy of final state. So what we can write? We can write ds1 this equals to ds2. So we have to substitute the value of ds in terms of two states. So here volume for the first state, volume remains constant and alpha becomes alpha 1. This is dp and cp becomes cp1 dt, and this is what? Minus v alpha 2 dp plus 1 by t cp2 dt. Okay, so that we can write from by using this relation. So let us simplify. So this will be what? This will be, if you take vdp common, then it becomes alpha 2 minus alpha 1, and if you take this dt upon t common, then it would become cp2 minus cp1. So what will be my dp dt is constant. S constant means, since we assume the constancy of entropy, so this becomes cp2 minus cp1 by tv alpha 2 minus alpha 1. Okay, so this is one dp dt entropy constant, we write it cp2 minus cp1 tv alpha 2 minus alpha 1, where the this 1 and 2 represents the initial and final state respectively. Okay, so this is, we arrive at this result by assuming the constancy of entropy. Now let us see what happens if we assume the constancy of volume. Okay, so what happens if we assume the constancy of volume? Okay, if we assume the constancy of volume, so let us see the constancy of volume. Let us see the constancy of volume. Okay, so let us assume volume is a function of, say, P and T, pressure and temperature. Okay, so since dV is a perfect differential, what we can write? Since dV is perfect, what we can write? dV, that we can write del V del P T constant dP, and this is del V del T P constant dt. So you multiply this term, can be written in this way: del V del P temperature constant dP V1 by V del V del T pressure constant dt. So what is this? This is compressibility factor. You know it, because if isothermal elasticity is this, then what will be the compressibility factor? 1 upon Et. So this means minus 1 by V del P T. So this is that term 1 by V del P T, because there is a minus, there will be a minus sign. So this term represents the compressibility factor, that is the reciprocal of isothermal elasticity. Okay, Et equals to 1 upon Kt. So this term can be written as Kt, provided there will be a minus sign. Okay, and this is what? This is volume expansion coefficient. Okay, simply. So this dV can be written in this way. Again, do what I did previously, that in second order phase transition, the volume remains constant. That means V1 equal to V2. As a result, dV1 equals to dV2. So we have to substitute the value in this equation. So let us see what will be the result. Okay, dear guys, if you don't subscribe my channel, then kindly subscribe my channel and share it to your friends and the nearest ones to get latest videos on physics. Okay, so if dV1 equals to dV2, then what is this? This becomes Kt becomes Kt1, say, and alpha becomes say alpha 1. Okay, and this becomes minus, because volume remains constant and also pressure and temperature constant, so it would be this V alpha 2 dt. ah V alpha 2 dt. So what would be the result if you take V dt common? Then it would be alpha 2 minus alpha 1, and if you take V dp common, that is kt2 minus kt1. Okay, V dt into alpha 2 minus alpha 1. Okay, fine. So V cancel. So what would be my dp dt volume constant? So my dp dt volume constant will be this alpha 2 minus alpha 1 kt2 minus kt1, alpha 2 minus alpha 1 divided by kt2 minus kt1. So this gives a name set 2. So previously, okay, so this gives name 2. So these are the two Ehrenfest equations of second order phase transition. Again I write it that dp dt s, this you can write as cp2 minus cp1 by tv alpha 2 minus alpha 1, and this is dp dt volume constant. This is equals to alpha 2 minus alpha 1 by kt2 minus kt1, where cp represents the specific heat, alpha volume expansivity, and kt isothermal compressibility factor. So these two represents the second order phase transition. Okay, so this is what about second order phase transition and Ehrenfest equation, and we will learn about second order phase transition in more details in phase transition and equilibrium chapter, which I will start later. Okay. So let us move to another issue. Now, by using Maxwell's relation, I will discuss about the differences between two specific heats. Okay. Previously, I did it. Now, by using the concept of Maxwell's relation, we use the different. We can check the difference between two specific heats. Okay. So, what we can write from first law? We can write from first law this. Okay. This is the first law of thermodynamics. Now let us take u as a function of volume and temperature. Okay, let us take u as a function of volume and temperature. Now since du is a perfect differential, that we can write as del u del v t dv del u del t v dt. Okay, du this equals to del u del v temperature constant dv plus del u del t volume constant dt. So substitute the value of du in equation 1. So what we get? dq this equals to, we will be able to take dv common, and if we take dv common, then it would become this. So this, okay, so dq will be this del u del t volume constant dt plus p plus del u del v temperature constant dv. So divide this equation by dt, divide this equation by dt, then this cancels, this goes. So del u del t volume constant, and what would become dv dt. So p plus del u del v temperature constant dv dt. Okay, now let us assume the constancy of pressure. Now we have to apply the pressure constancy, that is at constant pressure what happens, because in left hand side we have to bring cp, so it's only possible if we take pressure constant. So at constant pressure So at constant, because if we assume pressure constant, then the left hand side becomes Cp. So at constant pressure, this becomes what? This becomes del Q del T, pressure constant, and this becomes this, and this what becomes? This becomes this. So del U del V, temperature constant. This is del V del T, pressure constant. Okay. So this will be what? Now we will be able to get the general equation. Okay. We get the general equation for the difference between two specific heats. Okay. So left hand side, this term becomes Cp, and this we all know Cv. If you take it in left hand side, it becomes this. So this will be what? P plus del U del V, temperature constant, del V del T, pressure constant. So this is the general equation for the difference between the two specific heats. Okay. This represents the general equation for the difference of two specific heats. Okay. So general equation, this represents the general equation for difference of two specific heats. Okay. General equation for difference of two specific heats. So let us discuss the various cases. So suppose first of all we take ideal gas, and we studied previously that in lecture 5 or 6 I told that variation of internal energy with volume, and there I told that for a perfect gas this term vanishes. There is no variation of internal energy with volume for what? For perfect gas. So if you choose a perfect gas, then this term vanishes. So what would be the result? This will be simply P into del V del T, pressure constant. Okay. Now again apply this equation, PV equals to RT. So by keeping pressure constant, if you make differentiate this, then this becomes this. So this will be what? This will become R. Okay. So we see that it agrees with the actual result. Okay. So for a perfect gas, this term vanishes. So there remains P into del V del T, pressure constant, and by using PV equal to RT equation, we make a by keeping pressure constant, we differentiate this with respect to T, and we will get the result. Okay. So let us check what happens if the gas is a van der Waal gas or real gas. Okay. So what happens if the gas is a van der Waal? Okay. So for van der Waal gas, what we can write? P plus 1 mole van der Waal gas, we can write this. Okay. So at first multiply this, PV minus PV plus A by V minus AB by V square, this equals to RT. Okay. So differentiating this equation with respect to T, keeping pressure constant. So what becomes? This term is totally constant, so is 0. So this. Okay, and minus 1 by V square means plus 2 by V cube. So del V del T, pressure constant, this equals to R. So what we can write? Del V del T, pressure constant, means R by this P minus A by V square plus 2AB by V cube. Okay. So that we can write del V del T, pressure constant, that we can write as this term over in this way. Okay. So let us simplify this more and see what happens. Let us simplify this more and see what happens. So what will be my del V del T, pressure constant? We get it R by this P minus A by V square plus 2AB by V cube. So if we rearrange it, we can write in this way. Just look it. just we can look it. Okay, P plus A by V square, this. Now you substitute, for real gas we know P plus A by V square, this equals to RT by V minus V. So instead of P plus A by V square, substitute RT by V minus V. So minus 2A by V cube into V minus V. Now you take RT by V minus V common. So what will be become? If you take this, then 1 minus this becomes 2A by RT V cube, and there is a square term. So if you take RT by V minus V common, it will become this. Okay. Now what will be del V del T pressure constant? R into this V minus V goes in up, and this RT. Okay. And if we take this term multiplied by, okay, oh sorry, this becomes V minus V by T, RR cancels. Okay, and if we take it in numerator, this becomes RT V cube V minus V whole square to the power minus 1. Now you apply the binomial expansion, 1 minus x to the power minus 1, 1 plus x square. Now since this term is very small, we neglect the high order terms and only take the first term, that is 1 plus x. So just take the first term, 1 plus x, 2a by RT V cube into V minus V whole square. Okay. So this is the value of del V del T pressure constant. Okay. So what would be the difference Cp minus Cv? Now P plus del U del V temperature constant, and we previously derived that for real gases del U del V temperature constant is A by V square, that I told, and del V del T pressure constant means this. So 1 plus 2A by RT V cube into V minus V whole square. Okay, and P plus A by V square means RT by V minus V, and this is V minus V upon T, and that we can write 1 plus 2A by RT V cube into V minus V square. So this cancels, T cancels, R into this becomes 1 plus 2A by RT V cube into V minus V whole square. Or now if you apply this approximation, V is very much greater than V, then you can also ignore this term in the bracket. So it becomes V square and there is a V cube, so this term becomes 2A by RT V. So we simplify it and arrive at this result. You can also do up to this, it's okay, no problem if you do up to this. And you can also do up to this by assuming V very much greater than V. So thus we see today the Ehrenfest equation for second order phase transition and the difference between two specific heats by using Maxwell's relation and the special cases. Okay. Now in my next lecture I shall going to discuss few other problematic questions related to Helmholtz free energy, Gibbs free energy, enthalpy, that is based on thermodynamic potentials. Okay, thank you.